Hi everyone. All right, so today we're doing more accumulation, and the goal is to work with this problem. And I'm going to introduce or reintroduce a topic to you called an accumulation function. That's what this piece is right here. So, what is an accumulation function? Well, g of x is a function, and it's called an accumulation function because if you'll notice, it involves an integral. So, sometimes these are called functions involving integrals, but the input value is one of the bounds of the definite integral. So you'll notice that there's a 2 on the bottom, but the x is the input. So for example, if you were to plug in 5, g of 5, you'd plug it into the bound and you would accumulate from 2 to 5. And then f is some other function that's either given as a graph, which is we have in this case, which is the most common that we deal with in this class. It can be given as a table, but then we'd have to do an approximation if we wanted to find the accumulation, or it can be given as another function, as an equation, and then you would antiderive and then find the definite integral that way. But most of the time we see it in this class, they're defined by graphs. So, a few things. Remember, x is the variable. T is what we call a dummy variable because, for example, if you were to evaluate g of, not 2, let's do 3. If you were to evaluate g of 3 from 2 to 3, f of t dt, you would evaluate the integral. In this case, we're going to find the area under the curve. And then you would plug in, well, if you're doing it as an equation, you would do top minus bottom as the definite integral. Or you would accumulate the area under f from 2 to 3, and you get an answer. Long story short, you get a value. You're evaluating this, and t is not present in your solution. So t serves the purpose of allowing us to do the accumulation, but once you get an answer, that's your answer. That's why it's called a dummy variable. It's not really present in the problem once you do the evaluation. So we're going to go through this FRQ because it is a very good one for walking us through a lot of the things I'm going to ask you to find. First, there are some key things you should pay attention to when you are given an accumulation function such as this. The bottom bound tells you where to start accumulating. So if I were to plug in 2 to this accumulation function, we would have a definite integral with the bottom bound being the same as the top bound. And as we saw a lot last year, or if you just think about it as area from 2 to 2, that equals 0. So you can almost think of it as the bottom bound is kind of giving you an initial condition. It's telling you that the input of the bottom bound will yield an output of 0, which sometimes is important. But the point is the initial condition is built into the accumulation function. The other key component, because we're dealing with these in this calculus course, is how does g's rate of change and f relate to each other. So from last year, I told you the key thing to remember when you are dealing with accumulation functions and you want to start answering calculus type questions is to find the relationship between g prime and the accumulation function. So in other words, what is g prime of x equal to? Well, we know by the second fundamental theorem of calculus, if you take the antiderivative, well, the accumulation function, and take the derivative of it, they are inverses, and essentially they cancel each other out. And you are left with the inside function, top bound, plugged in, and then you don't have the bottom bound because when you take the antiderivative and then derive it, you are getting a constant that then goes to 0. So in other words, the relationship looks just like this. The derivative of g is equal to f of x. That just means that this, the graph of f, is the derivative graph. So we are dealing with a derivative graph here, and now we're kind of back to the last lesson where we had a velocity curve or a derivative curve, and by analyzing the derivative curve, we can answer questions about the original. So that's the goal. That's what we're trying to do. And then you can take this one step farther and say that the second derivative of g is equal to the first derivative of x, or f. And so I always like to draw these two or write these two relationships immediately. The AP test gives, I graded last year, and one of the points was writing this. So by writing it, excuse me, you'll get your first point likely. All right, but let's take a look. Notice a bunch of triangles. Why on earth did they give us triangles? Because they want us to be able to find the area geometrically. If it was a smooth curve, we'd have to use antiderivatives, and we'd have to have the equation. If it was a table, we'd have to approximate using Riemann sums, but it's a bunch of triangles. So we're going to be adding up probably a bunch of triangles. And remember, if it's above the x-axis, it's positive. You're accumulating positive area. If it's below, it's negative area. It means the original function is going down. So does G have a relative min, a relative max, or neither at 10? So remember, it's asking about G, and this is G prime's graph. So G prime in this problem goes from negative or below the x-axis to below. It doesn't change sign. So if that's the case, it's kind of doing this in the original. It's going down, leveling out, and going back down. So this is relative max, relative min, or neither. This would be a neither case because we don't change from positive to negative in the derivative, which means we don't change from increasing to decreasing in the original. So this is a neither situation, and you would explain it just by how I did. Pretty common question. So a more interesting question would be, is there a relative min or a relative max at 6? Well, look, the derivative graph, the derivative of G, otherwise known as f, goes from positive to negative. So if the derivative graph goes from positive to negative, that means the original went from increasing to decreasing, and that's where you'd have a max. You'd have a min here at -2 because the derivative went from negative to positive. That means the original function went from decreasing to increasing. So pretty typical question they like to ask. B says, does the graph of G have a point of inflection at 4? So right here. So this is the derivative graph. And the one key thing I keep telling you to remember, don't say there are inflection points where the derivative has a critical point. That's one way to locate them. But the true definition of inflection point is that phrase that I keep reminding you of that we saw a lot last quarter. You need to find where G prime goes from increasing to decreasing or vice versa. And does this graph do that here? Does G prime go from increasing to decreasing? Absolutely. We went from increasing to decreasing. So yes, there is an inflection point at x equals 4. There's also an inflection point at 2, at 0, at 8, at 10, and at 12. And the one at 10 makes sense because going back to what we said in part A, look, we had a change in concavity from concave up to concave down, from increasing to decreasing in the derivative. So yes, that is also an inflection point at 10. Find the absolute minimum value and the absolute maximum value of G. Okay, so this is that big thing from last year that I love to do. So I'm going to, and by the way, you're allowed to do what we've done in A and B because you've made these relationships. You have to state this, at least this first part. Otherwise, you're not allowed to talk about G prime because where does G prime? You have to show that G prime is the same as F, and then you're allowed to reference G prime or F at any point in this. All right, but part, I'm going to get rid of it so I have space. Part C is the big part. This is where all the accumulation happens. So, part C says, find the absolute min and absolute max. As soon as you see the word absolute, you need to talk about candidates. Candidates. Remember, there are some places where if there's an absolute max or an absolute min, and if we're on a closed interval, we have to have a max or min, absolute max or min, because of the extreme value theorem. The extreme value theorem says if you have a differentiable function, even a continuous function actually, over an interval, closed interval, then there has to be an absolute maximum value and an absolute minimum value. So where are the potential places? Well, we're saying over the interval -4 to 12. That means those are your first two candidates. We need to find G of -4, and we need to find G of 12. Your endpoints are two of your candidates. So you always, always, always list the endpoints. But on top of that, you also need to list your critical points, which are the roots of the derivative. So there are a lot of them in this problem. G of -2, G of 2, G of 6, and G of 10. Now, some of you may be saying, I don't need to include 10 because it's not a relative max or min. It was a neither. It can't be an absolute if it was a neither relative max or relative min. And you could say that, but I have, again, trying to give you what the AP test is looking for. It's just easier to list all of them and find their values because they are very particular about how you eliminate candidates. If you can find these values easily, just find these values. So these are your critical points. These were your end points. A little weird E. All right, so we got to start accumulating and finding all these. Any of these easy ones? Well, from back what we started with, here's the accumulation function. I erased it sadly. But remember, when I plugged in 2, I got 0. So that's the free one. All right, let's move forward. I think that's easier. G of 6. Now, when we're doing normal accumulation with a derivative graph, they have to give us an initial condition, and we have to do initial condition plus accumulation. When you're given an accumulation function, remember I said the initial condition is built in. So really, you don't have to worry about including the initial condition because it's included for you. So all you have to do is plug 6 into your bound and find the accumulation from 2 to 6. And again, if this was a table, you'd do a Riemann sum. If this was an equation, you'd find the antiderivative and then top minus bottom. But this is a graph, so we need to accumulate this area. Clear some of this. We need to clear or find the area under the curve from 2 to 6. This is a triangle with, be careful, it's a little out of scale. Base 4, height, oh, it's not bad actually. Base 4, height 4, so this is 16, but divided by 2, so this looks like 8. And we just kind of go along and get all these values. All right, so how about 10? Well, same deal. We accumulate from 2 to 10, f of t dt. And that just says find the area from 2 to 10. And look at this, we get a negative 8. So the original function went up and then back down at 2. So this is negative 8. Nope, sorry. 8 minus 8, which is 0. And then what happens? Well, to get 12, because that's our other endpoint, it looks like we have half of 1, so it's negative 4. So we went down 4 more to get to 12. So you could, again, go 2 to 12 f of t dt. And that would be the two triangles which canceled each other out, and then down 4 more. So down 4 more. All right, so now we got to do this in the other direction, which is slightly trickier. Let's start with g of negative 2. So again, you're plugging in to the x value for the bound, and you get negative 2 in the top. Do not try to accumulate area when your bounds are out of order. It means to accumulate backwards, which is totally fine if you know to do that. But the way that I like to remember what to do is I want my bound to be in the correct order from left to right. So we can fix that by, as we've seen before, flipping the bounds and making the integral negative. And that will allow us to find the real area. So find the area like normal, get your answer, and then make it negative. Sometimes you're going to get a negative area, and then you're going to have to make it negative because you pulled the symbol in front by switching the bounds. And then you'll have to take the opposite of that value. But in this case, negative 2 to 2, we have an area of 8. So it's 8, but remember it is negative 8 because I have to remember the negative from when I flip the bounds. And last one, we have from 2 to negative 4, f of t dt, which is, again, out of order bounds. So I'm going to flip the bounds, accumulate from left to right, and make it negative. Find whatever the answer is after I add my integrals, or after I add my areas, and then make it negative. So from negative 4 to 2, I have this area, which is a negative 4, plus a 8 is positive 4. So the total area from negative 4 to 2 is 4, but then I have to flip it and make it negative. So negative 4. And lo and behold, we have all of our values. At this stage, we can identify the absolute max and the absolute min. And remember, this is called the candidates test because the absolute max and the absolute min have to be one of these values. So it's not like you're missing out on anything. These are the values it has to be. So it looks like we have an absolute min, minimum value of negative 8. So be careful what they're asking for. find the absolute minimum value. The value is -8 and it occurred at -2. The absolute maximum value is 8 and it occurred at x equals 6. And that's one of the biggest parts of these FRQs is finding the absolute maxes and absolute mins given a derivative graph or given an accumulation function and the graph of the internal function. The last one's kind of cool. I'm actually not going to do it. We'll save it for another time. You're just basically, once you have all this information and they want to know where is the original function less than 0, you can kind of piece all this together to get a sketch of the original. But I'm going to stop here on this one. And then I may ask you about this in class next time. See if anyone can get an answer. But this is what I care about. Okay. This is the part where I want you to be able to talk about the maxes and mins, relative maxes and mins of the original function, find the inflection points of the original function, and find the candidates for the absolute max and absolute min, and then evaluate these values using accumulation to find the actual values. All right, and that is it. Goodbye.